So physics for chemists, we're going to look at waves. We'll have a think about the following things. Wave descriptions, we'll look at the words used to describe waves and their various properties. We'll look at wave equations, calculations based on them, harmonics, interference and diffraction. So waves don't move stuff from place to place, they move energy from place to place. So if I try and be technical here and set my pen up. Okay, and waves are defined as periodic oscillations. So periodic just means over a regular time interval. There are two types, transverse and longitudinal. Now transverse waves include electromagnetic waves, S waves for earthquakes, and water waves. They're the ones where the direction of oscillation is perpendicular to the direction of travel. So transverse are what you think of as a wave. Longitudinal, which includes sound waves and P waves, the other earthquake type of wave, that's where there's compressions and rarefactions. Okay, so the direction of propagation and the direction of oscillation are the same. The reason, as a chemist, that you want to know a little bit about waves is that it's hugely relevant to chemistry, for spectroscopy, for colours, for bonding, and you know, as it says here, an electron in an orbital can be regarded as a standing wave. It's true. Equations of waves. So the speed of light, c, nu lambda. The speed of an electromagnetic wave is, in this case, using this terminology, is equal to the frequency times wavelength. Energy carried by a wave, this is the Planck equation, energy per photon is Planck's constant, which you can look up, scary number, times the frequency of the wave. And we know that light has properties of both a particle and a wave, wave-particle duality. For transverse waves, we need to think about what is meant by the words period, amplitude, wavelength, and frequency. So, period is the time taken for one complete oscillation. And if we try and define amplitude, then it's the maximum displacement from equilibrium. And the units, the size you need, will depend on what kind of wave it is. Could be nanometers or kilometers. No, perhaps not kilometers, but meters. So the amplitude can be defined here. Okay, the distance from the mean amplitude to this is called a peak, and this is called a trough. Okay, so that distance there is amplitude. If we try and define wavelength, then it's the distance between two adjacent identical points on the waveform. And in this particular case, I've drawn it as follows, from peak to peak, wavelength lambda, a Greek L. Define frequency. Well, the frequency is the number of complete cycles or oscillations per unit time. Frequency has dimensions of time to the -1, and it's got units of seconds to the -1, very commonly, and you can often write that as a hertz, Hz. 1 s to the -1 is the same as 1 hertz. Very important formula. Frequency is the same as 1 divided by the period, okay, the inverse of the period. The electromagnetic spectrum. So remember that there are all different types of colours, okay, in the electromagnetic spectrum. There's radio waves and microwaves and infrared and visible and ultraviolet and X-rays and gamma rays. We get excited about visible because our eyes can detect that, but all of the waves really just on a continuum, and they all have the same basic properties. Red light has got the longest wavelength, and blue light has got the shortest wavelength. Electromagnetic radiation, for example light, is said to have two vectors. It's got a magnetic vector and an electrical vector. And you've got two mutually perpendicular oscillating waves. And they're going, there's one going in that direction, there's one going in this direction at the same time. And the speed of an electromagnetic wave, often written as c, in a vacuum, is almost 3 × 10⁸ meters per second. And remember this formula, c is equal to nu lambda. Harmonics, really important this. The first harmonic, what I'm trying to describe here is two nodes here and here, and an oscillating wire or string in between to show the wave. So that will be called the fundamental frequency. You can have the second and the third harmonic on top of that, and they would look like this. And you need to be familiar with certain bits of terminology. So what you've got there is an antinode and a node. Antinode is where the amplitude is a maximum. This is hugely important in chemistry. If you want to imagine what's meant by energy levels of electrons, it's often very hard to get your head around what that might be. Well, what's meant by an energy level, a different energy level, you can regard, if you say an electron's got wave-like properties, then the first energy level can be regarded as this, the fundamental frequency, or the first harmonic, and then the next energy level up for that electron could be regarded as this harmonic here, the second harmonic, and so on. And that's been shown to be so experimentally as well. More on harmonics. A waveform with a fundamental wavelength, lambda, has harmonics with wavelengths that are lambda by 2, lambda by 3, lambda by 4, and so on. And so in the case of this very commonly used laser, the fundamental wavelength is 1064 nanometers, but you can have a second harmonic at 532 and a third at 355, which is so going from green to near UV, and there's a fourth which is deep into the UV region at 266 nanometers as well. So it's showing you that these harmonics are real for electromagnetic waves, in this case visible, or infrared, visible, and UV. First harmonic, or the fundamental, is the same. Fundamental wavelength, I'm sorry if I said the frequency earlier. Interference. Take two waves that are said to be in phase. Okay, so as one is going up, the other's going up. So one goes down, the other's going down, and so on. So they're in phase like this. Two perfectly in phase waves, where they meet, are said to undergo constructive interference. And the product is going to be a new wave with twice the amplitude. So you've got amplitude A, they meet, and so you have twice that amplitude in the resultant wave. It's actually the sum of the amplitudes of the interfering waves. I was just keeping the numbers neat there. If you take it the other way round, amplitude A and amplitude A again, but they're now meeting what we say in antiphase, so a peak meets a trough in this particular case, then what you get is destructive interference that you can represent like this. This is used in noise-cancelling headphones and in some luxury cars and in passenger airliners where you have electronic circuits and there's a microphone that picks up the background noise, and then an electronic circuit generates the same sound wave in antiphase, and it has the effect of cancelling out that background noise of the wind noise or the engine or what have you. So that's how that's done. In chemistry, you might wonder why that's of any interest at all. If you take electrons as waves and you say they have a wave function, where you have two waves meeting and their wave function is in phase, you form a chemical bond, and where you have two electrons meeting and their wave functions are out of phase, then you have an antibond. That's Linus Pauling's work on what a chemical bond is. So perfectly destructive interference results in a zero amplitude wave. There is no wave, total cancellation. Just taking that a bit further, if you have a wave, this is still meeting in phase, but you've got a wave with this is actually meeting out of phase, I beg your pardon, twice the amplitude 2A meets an amplitude with amplitude A, a wave with amplitude A, then what you get here is destructive interference, but you have a subtraction effect. So a 2A wave, amplitude of 2A is meeting amplitude of A out of phase, the resultant wave has got an amplitude of A for its amplitude. A reduced amplitude wave. If you want, as I say, go nuts here, superposition. When two waves travel together, the amplitude at a point is the vector sum of the two amplitudes at that point. So if you take here, you can see that there's the amplitude of this point here is added onto the amplitude of this point here, and then the total amplitude of the new combined wave is much higher up. You can have a look at that diagram and see that it makes sense yourself. The sine wave, often not the x-axis often isn't written with degrees, it's written in radians. So that's just showing you the sine wave using pi, 2 pi, 3 pi, 4 pi radians along the x-axis for you, and amplitude and wavelength. Probably the most commonly used wave function. So that's just to remind you what it looks like. Thank you.